Okay, so a quick little video about catalysts. So what do you need to know about catalysts? Well, at GCSE there are two definitions that you need to know for catalysts, and they are out in front of you. We have catalyst. Okay, well that seems like it's a catalyst. What is this all about? This is the definition of what a catalyst is. What a catalyst is. What is a catalyst? It is a substance that increases the rate of a reaction but is chemically unchanged at the end of the reaction. That is what a catalyst is. We also have this definition over here, which is catalysis, also known as what a catalyst does. Or some people would say how it does it. So this is the process by which a catalyst works. A catalyst provides an alternative reaction pathway, we'll talk about that in a sec, with a lower activation energy. Again, we'll look at that visually in a moment. These are both 2-mark definitions, and you need to get the right one in the right place. What a catalyst is this one over here. What a catalyst does is this one over here. Now, there is one slight problem. Sometimes you come across a 3-mark definition for a catalyst at GCSE. In that situation, write both definitions. You're going to be writing down 4 marking points, of which you will gain marks for 3 of them. At GCSE, we really only look at one catalyzed reaction in a great deal of detail outside of sort of industrial chemistry, and that is the decomposition, i.e. breaking down, of hydrogen peroxide. Now there's a couple of formula here that you need to learn. There is an equation that you need to learn. So what is the reaction for the decomposition of hydrogen peroxide? I'm not going to write out the word equation. I'm going to jump straight in with the balanced chemical equation, also known as just chemical equation. So hydrogen peroxide is H2O2, and that decomposes to give H2O and oxygen. If we look at this, it's clearly not balanced, so we need to balance it, and we can balance it quite easily like this. The key to this reaction, though, is that oxygen is released, and oxygen is obviously a gas, which makes this reaction quite easy to follow because we can collect the gas. We can collect the gas using a gas syringe attached to a conical flask where the reaction is happening, or we can attach a delivery tube to the conical flask in which the reaction is happening and collect the oxygen gas by downward displacement of water. What that does allow us to do is collect data like this. Volume of gas released against time. And I will do a separate video as to the shape of these graphs and why these graphs look like they do. Now, in reality, this reaction, the decomposition of hydrogen peroxide, is exceptionally slow if you do not use a catalyst. So, what catalyst do we use and how do we know it's a catalyst? Well, the catalyst we use is something called manganese 4 oxide, which is MnO2. Please do not get manganese and magnesium confused. They are completely different things. So this is manganese 4 oxide. This is the catalyst for this reaction over here. And how do we know it works? Well, if we throw some powdered manganese 4 oxide into a solution containing hydrogen peroxide, we will get a very rapid decomposition. We will see gas being given off much quicker. i.e., if we look at a reaction graph like the one down below, because the rate of reaction is given by the gradient we would see a much steeper gradient to begin with. And assuming we're using all the same amounts of reagent, it would finish at the same height. Now, it's not easy to get this perfectly on, but there we go, that's not bad. So this would be with a catalyst. Always, always, always label your lines on your graph. I've seen so many people lose up 4 or 6 marks by sketching perfect lines on graphs and then not labeling them. And this one would be without a catalyst. Let's just run that through one more time. With a catalyst, we get an increased rate of reaction. The rate of reaction on this sort of graph is given by the steepness, the gradient of the line. Cool. We're going to do one last thing. I did promise that we would talk about the alternative reaction pathway up in the catalyst, up in the does definition, and the lower activation energy. Now, this bit is given over on the left-hand side, bottom left of the screen, and this is TAS only, although it does really help the explanation or the understanding if you are doing DAS. So what have we got here? We've got an energy level diagram. We have, let's find a highlighter, we have the energy of our reactants shown here, and the energy of our products shown here. Now, if we look at that, the reactants are higher in energy than the products, so energy is going to be given out when this reaction occurs, so this is going to be an exothermic reaction. Heat energy is going to be given out. Okay. So, what have we got on this line? Well, let's maintain our blue highlighter. We have this thing here that goes all the way up and all the way down. What on earth is that? Well, that is the reaction profile or reaction pathway, which mirrors the language we used up here, reaction pathway. So this is reaction profile or pathway. And this would be without a catalyst. That would be without a catalyst. And you see we have an activation energy that is drawn on in red. So what I'm going to do, I'm going to get, let's use a green pen. I'm going to draw on the reaction profile with a catalyst. What's that going to look like? Well, it's going to start in the same place and it's going to end in the same place because we've got the same reactants and the same products. Nothing's chemically changed, but my reaction pathway, reaction pathway or profile, but I'll use pathway here because it mirrors the definition, with a catalyst. You can see that it is different, it is alternative. You could also hopefully see that we have a lower activation energy, i.e. the amount of energy we need to get into the products to get them to effectively hop over this hump and get down into products, give the reactants and get them over to products, is going to be less. That much with a catalyst, that much energy needed to get the reaction to go with the catalyst, versus all of that energy without the catalyst. So, in summary, catalysts, you need to learn 2 definitions, what the catalyst is, what the catalyst does. You need to learn very well the example for the decomposition of hydrogen peroxide, where you need to know that manganese oxide, or manganese 4 oxide more correctly, is the catalyst for that. If we were trying to test other catalysts, what we would do is we would literally just throw other catalysts in and draw the rate graphs for them. The ones that have the steeper gradient are going to be the more effective catalysts. If there is absolutely no change in the gradient with or without the catalyst, so-called catalyst that you're testing, then that catalyst isn't a catalyst, it's not working. But with the manganese 4 oxide, it's definitely a catalyst and it definitely works. It will increase the rate. How does it increase the rate of reaction? by providing an alternative reaction pathway with a lower activation energy, which if you're studying task chemistry, you'll have to be able to draw, which is that little energy level diagram on the left. Good. Go away, make your own notes on this, make sure you learn the definitions, make sure you learn the reaction chemistry, the chemical equations, and the reagents, and the name of the catalyst. Cool.